Hello, again with the finite element analysis class. For the last week, we tried to explain you the introduction of theory of elasticity and basic consumptions and some of approximations to describe different type of materials. So today I will try to finalize the fundamentals of elasticity theory, and if we have enough time we will try to continue with finite element analysis introduction. And let's start with background of finite element analysis first, and then I will continue with elasticity. As I told you in the last few weeks, finite element method is not a new method. It's covering about maybe 70-60 years. In 1950s, solution of large number of simultaneous equations became possible because of the digital computer, and in the beginning of 1960, a guy called Ray Clough, he just first published his paper talking about finite element method. In 1965, there is a kind of first conference. The people were talking about the finite elements, and this is the critical date in 1967. A very famous professor, Zienkiewicz, he was published the first book about the finite element method, and it's just started to develop 1970s, and especially in the 70s, some softwares and codes about finite element solutions, which are Abacus, Nastran, ANSYS, etc., they are continue today. And some of the people try to embed fluid flow and thermal analysis through the FE developed softwares. And now we are still trying to develop many different areas, coupled field analysis, explicit dynamics, etc., etc., together, and new type of materials, material modeling. And if we talk about the numerical methods, and finite element method, it's a numerical method also, we can say that we have got a few more methods. For example, finite difference method, finite volume method, and I told especially finite element method that we focused on, and boundary element method, meshless methods, etc., etc. And recently, for the fracture mechanics, extended finite element method. It just continues, and the basic consumption of the numerical methods, they just try to explain the displacement function. Displacement function is very important. So, for example, we can say that a displacement function, let me write here, it is d4 omega over dx to the power 4 should be equal to q over IA. And you can remember this from the beam equations, fourth order differential equation. And we try to draw the displacement function. Instead of drawing, let me put you a figure. So the function omega is equal to fx can be figurized in this way. And we have to write again omega is equal to fx and this one here to explain the concept of finite difference method and a displacement function variable, which is omega. And this is the description of omega. And we try to write a displacement function here, like delta omega, we can say, should be equal to fx plus delta x minus fx. This is the next point. This is the point description. So after this, we can write d omega over dx equal to LT delta x is going to 0 and delta omega over delta x. This is the basics of function, and it is equal to t again delta x is equal to 0 f x plus delta x minus fx over delta x, and finally we got 1 over h omega I plus 1 minus omega I. So we try to use the differential equations to solve it. Let me show you. Let me put the equations. I think I can find it here. Yes, this one is okay, I think. Yes, we use the differential equations, second order, third order, and we will get here 1 over h to the power 3 omega I plus 3 minus 3 omega I plus 2 plus 3 omega I plus 1 minus omega I. I try to explain the basics. This is not so important for now. Maybe later you will use it. And after this, because we want to reach the fourth order, for example, for the beam analysis, you need fourth order. And if you have the moment equation, you need second order. Fourth order is describing the spread of weight, spreaded weight. And let me show you the final equation, the fourth order. This one will be the fourth. This is the final and fourth one. Yeah, after that, we can write the finite difference form, not finite element, because these are the basis of finite difference. And let me show you this one. And this is the description of finite difference. The expression is in fourth order, and maybe I can show you the finite difference equation at node I here. How is the equation made? Let me clear here. Yeah. This one is for the node I, finite difference equation. And this is the equation. Fourth order equation. Yes, this is just a simple introduction of finite difference, but we won't use it in this class. Maybe some special issues, but not from now. Later. Let me talk about a little bit elements and nodes. We have already told many things about this, but regular and irregular style, very basic shape. For example, this one is very simple shape. If you want to mesh it, it will be very easy, like this. We will just try to create mesh with equal numbers first, maybe, and then to reach more detail, you can increase the number of meshes, or for decreasing the time, you can make a coarser mesh. For example, I want to make much more precise description of this area. So I can make this zone refiner like this. If I need to get more detailed answers from here, I will change the meshes like this. And this one will focus the solution domain. This is global, all of the domain, and this one we are trying to focus here maybe. So we increase the number of the elements, and we got a finer mesh situation here. But if we change the domain and it is not a regular shape, let me clear. I want to show you a kind of footprint here. This is a weird model, so I try to make a mesh, but if you leave it to software, it will create something like that, composed of generally quadrilateral elements. Maybe it can be again composed by triangular elements, etc., etc. It's up to the computer software. But if you look at the shapes, the mesh generation is composed of irregular elements. It's not a perfect square or something. Because of the edges, the shape of the mesh elements will change, and it's try to be adapted the system to the mesh and the size of it. And this one is describing the domain, the working zone. And after this, we need to answer the degrees of freedom of the system. A structure can have infinite number of displacement, but approximation with a reasonable level of accuracy can be achieved by assuming a limited number of displacements. After that, this finite number of displacement is the number of degrees of freedom of the structure. Let me say, the truss member will undergo only actional deformation, truss and axial deformation. Therefore, the degrees of freedom of a truss member with respect to its own coordinate system will be 1 at each node, because the truss member can be deformed on its axis. Maybe we can say if a two-dimension structure, 2D, we design with truss elements, then the deformation with respect to the structural coordinate system will be 2, and therefore degrees of freedom will also become 2. Why? Because we increase the axis. We are using 2D now. Because of that, the degrees of freedom will be again 2. And the degrees of freedom for various types of element, maybe we can show a figure for you. To explain it, we are going to use UVW for the displacements, and for the rotations, theta, x, y, and z. And yeah, this figure, let me put it here. Yes, here. And I'm going to add a few more steps. Yes. Let me talk about it a little bit. These ones are describing the displacement and rotation definitions. And I'm talking about the degrees of freedom for various elements. For example, we have got 2D truss system, as I told you before. One axis displacement u, the other one v. I'm not giving the global one, but you should know it. The global coordinate system is x, y, z. It's already known. X, y, and z. But the local coordinate, especially for writing the code, you shouldn't write x, y, z. You have to change it, because this one is global. When you create a rotation with these axes, you will get an angle with the global coordinate system. So this one for the 2D. And we have got 2D beam, not truss. This time, this one is going to give us one displacement in the direction of V and rotation around Z. This is moment vector of Z. So this will give us theta Z around the axis Z. This is beam definition. These definitions are very important. You have to know them in terms of describing the solution constitutive equations. You have to use the coordinate systems considering these definitions. And for the 3D truss, we have got 2D, we have got 3D. It means, you can understand from the figure, there is no angle rotation. So truss is capable just with axial deformation displacement. So we can use U, V, and W. And for the 2D frame, it is again a kind of beam. But this time, frame. You can use a few beams at the same time. So we have got one displacement U, the other displacement V, and rotation around Z is theta Z. And this time we increase the frame. So we have got 2D grid. And we have one displacement, two angle rotations around Z and axis of X. Finally, 3D frame, we got 1, 2, 3 displacements, and again 1, 2, and 3 rotations. So if we come to membrane definition, you got two displacements, U and V. For the plate definition, not a plane, be careful. Plane is a different thing. This one is plane. This one is plane. But plate can be in a different angles, but there is no thickness. But it is again a kind of plane. We have got one displacement and two rotations, which is kind of 2D grid. And shell, as I told you in this one's description, we said that there is no thickness, of course, but we can give an additional thickness to the plates. But when you are using shell, yes, you can give additional thickness, but you cannot see on the computer. It's only a representation. For trying to create a solution, we have got no thickness, especially with the CAD model. Shell, so we have got 1, 2, 3 displacements and 1, 2 angle rotations. a solid brick, 1, 2, and 3. Displacements. Yes, this one is very important. Let me increase and change the system, and let me start with idealization of a continuum. So because of that, I will give you a 3D description. Like here. Yes. This one, a 3D description. It just shows us 3D description. So this one, irregular shaped general solid element. And when we try to make it simpler, initially we try regular solid. Can we make regular solids and combine them together to create general solid? We got x, y, z coordinates, but when talking about the solid, what is the simple form of it? Truss, beam, or whatever it is. If you remember the other figures before this one, you have to think initially, which type of it should I express for my finite element code? Maybe a beam, but the shape is important. Beam can be defined a little bit longer, and the cross section will be much less than the longitudinal areas. So this can be described as beam. It's up to your problem. Or a membrane. In plane, only axial. These are coming again from the description that I have shown to you. And plane, out of plane, it means out of plane. It's going out. And shell, there is bending available here, 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 everywhere. We can bend this surface like this. It's a kind of parachute. There is no thickness, but if you hold here from the four edges and make it flat, maybe you will get a plane. But during usage of parachute, you will get something like that because air is inside. So this time, this one is in 3D. So when you are using the elements that I have told to you, you can reach to these continuum elements. So after that, you will discretize the elements and you will mesh it, it means. So you can get a meshed domain. For example, I will going to show you again the initial domain to you. For example, an irregular shape again, meshed with triangular elements. But this time, I have used quadrilateral elements 1, 2, 3, and 4. And the edges won't be like that. The edge of the system will be changed like this. Let me use this one, for example. Yes, something like that. It just continues. And we have got no zoom like here anymore. Because of our mesh quality, these are gone. So you need to create a discretization of your system. If this is not so important, you can erase them. And generally, we are using something like this. And triangular. Instead of triangular, if the shape is so weird, of course, the computer will try to use triangular elements, but you need to push them. You need to force it to use quadrilateral or in 3D hexahedral elements. Yes, let's talk about the concept of finite element analysis and continue with a little bit definition of displacement, and again we need to explain some elastic definitions. Let me tell you for the initial consumption. The classical and actual structure can be defined with the partial differential equation like this. Yes. This is the actual structure, real. And in terms of stresses and domain function of F, which is giving us the forces or etc. And after this classical and actual structure definition, we will create some assumptions like equilibrium equations or stress-strain law, and maybe the compatibility conditions, and which is going to give us the principles of virtual work. Let me find it for you. Yeah. Yes. After this, we will get some assumptions. And this is the basic. If you remember the Hooke's law, we will have, remember, E is equal to sigma over epsilon. But for using these equations, when you try to write E here, you need a transpose of the matrix to write this equation. So we will get this one. Omega is describing the domain of the system. And this is the basics of principles of virtual work. So, for adaptating the equations to the finite element method, I have already told it to you. which is a kind of spring equation. F is equal to K multiplied by U. This is the repetition of it. Yes, it means we will get here finite element structural model. F is defining the force vector. K is defining stiffness matrix, and D is defining deformation or displacement again vector. Let me write it also. So we will try to find the displacement in order to prepare the model first. Displacement, and then strains, and then finally the stress. But using the displacement, after finding it, you are able to find the internal forces also. So it means that for the experimental setups also, for during the real life, we need to find the displacements. Like during the tensile test, you will read the displacements of the sample by a sensor, for example. And then you will measure the forces again with the same steps. If there is no additional computational equations in your tensile test machine, it will only give to you the deformation results and the forces. That's it. And by getting those values, for example, up to the quality of your test setup, it will give, for example, the cheap one will give you a few results in a second, but very expensive one maybe give you 20 results, 30 results, I don't know, it's up to the selection. And you will get millions of rows of the tensile test results. So this one is also working with the same ideology. First one, we will get the deformations, but if you want to get more precise results, you will need to use extensometer systems, maybe camera extensometer or digital image correlation systems for getting more precise deformation results. Not in just 1D, for the transverse zone or lateral part of the sample. Let me draw it to you. If this is the sample, sorry. If this is the sample and direction, we have direction of y and direction of x in global. But we can say 1 in local, 2 in global. You have got a result for 2 and 1. But 1, how can we get the result of 1? Maybe you need to use strain gauges. I'm sorry, I have drawn in the wrong direction. Yes, for this direction, this strain gauge will give you the results. For the 2 direction or direction of 2, you will get the results with this strain gauge or the digital image correlation or laser extensometer, etc. So this is going to give you an ability to find out the Poisson ratio of 1, 2. And if you are a capability to make or repeat the test in the direction of z. So you will get 1, 2, 3, 1, and 2, 3 of the Poisson ratios. And again, I'm talking about the Young modulus also. Yeah, for this one, let me change the system like this. If we have got a force vector is equal to K matrix multiplied by D vector, I'm going to leave the D alone. So we will get vector of D is equal to inverse of K matrix multiplied by force vector. So let me talk about the parameters, maybe for different cases. Maybe let me tell you about the solid one. The property of the solid matrix can be described by stiffness matrix, but in fluid one you will use viscosity matrix, or for the thermal solutions you will use conductivity matrix. And the action for the solid elements, you need loads. For the fluids, you will need body forces. And thermal, you will need an heat action. And considering these ones, we will get a response of displacement for the solid elements. And we will get pressure or velocity response for the fluid and temperature response for the thermal analysis. We have talked a lot about the advantages, disadvantages, accuracy, etc. So let me continue with the stress and equilibrium, which I have already given to you. I try to remember. Let's try to find the basic stress on an infinitesimal element. Like I found it. Let me show you this one. Yes. This is an infinitesimal element, unit element, let me say. And I have given these stresses on it. And these are the stresses, but the other ones, the effect of the other ways. This one here, I'm talking about Z, but it's again in the plane of ZY. Because of that, I have added tau ZY over dy multiplied by dy. And these are based on the same ideology again. Yes, continue. And for trying to give the equation considering the finite difference, and we will gonna adaptate the system to the finite element method again to describe the domain of our structure. Let me give you an equation. This one is going to tell us again for the direction of dx, dy and dz all together, but I am trying to describe it in terms of x-axis. So we will have d sigma x over dx and 3 dimensions, But after that, there is not a one way. There is x and y, and finally x and z. So because we are using two axes, the normal stress becomes shear stress. And at the last part of the equation, we will get the body loads of the system, forces along the direction maybe, and which is giving us the x forces of the domain described by omega. So let me put these equations into one for each axis. Let me make it clear. D sigma x over dx plus d tau xy, or considering this one, we should write yx over dy plus, again for the z, d tau zx over dz is equal to minus f omega x. This is for x direction. And we will repeat it for the y direction. I'm going to write just a few parts. Let me start with yes, we can repeat it for the y and z direction. So we need to start with d tau x and z because we are using y in terms of dx. Again, the same. Plus, this time, the same axis. Because of that, we are using d sigma y over dy plus d tau zy over dz. We have forgotten this one. And it is equal f sigma y, again d tau. Oh, sorry. We have written this one wrong and nobody told me. Let me make it clear. This should be y. Yes. And this one should be x and z over dx. Again, d tau yz over dy plus d sigma z over dz is equal to minus f and omega z. Yes, this is the open form of a stress system, and we will try to create a satisfying moment equations, and maybe we can say that f omega y and f omega z are the component of body forces along the y and z directions, satisfying these equations, we can say, maybe, let's write it, sigma mx is equal to 0, and sigma my again is equal to 0. Finally, for the z, again, it is equal to 0. And considering this one, we can obtain tau xy must equal to tau yx. And the same thing with tau yz is equal to tau zy, and finally tau xz is equal to tau zx. So we can repeat these equations again. Repeat, I'm talking about these ones. And now we can try to write, maybe let's assume an element of area. Yes, let me write this one considering let me clear here. And considering all of these and assuming an area of the element with delta and also we should give the forces for the area of the system. Force x and force y, and for the z the same thing. We can write an equilibrium, and we can say that these are the components of external forces per unit area, which are acting on the surface. I'm talking about these. And considering these ones, let me write it. Sigma xl tau xy m and tau zx n should be equal to f gamma x. Again for the y, tau xyl plus sigma ym plus tau yz n. This time is equal to f gamma y, and finally tau zx l plus tau yz m plus sigma z n. is equal to F gamma Z. Yes, we can say for L, M, and R are the direction cosines, which are describing an axis is going to give a projection onto the x, y, z with the help of those cosines which are belong to those axes. So we will get this one now. Let me show you. This means the same thing. Forces acting on an element on the boundary. And to describe strain displacement relations, we are using x is equal to x plus u. So u means u is equal to x minus x, but let me show you like this so you can understand much better. Yeah. For example, we have x hat is equal to x plus u. So I need to find u as a displacement with the help of our equations. You have x. We can write x2 minus x1 also. And these are the same with y. You will write it for y is equal to, instead of y, we will write v. v is equal to y hat minus y. And for the z, we will write w or omega is equal to z hat minus z. So after that, we will get these equations. Let me write here. For the epsilon x, we can write du over dx. For the epsilon y, you will get dv over dy. And finally, epsilon z is equal to d omega over dz. And you will get the deformation after this. How? Let me show to you. After the application, we will get this situation. There is r vector, and this is the vector of r dot or r hat. You will get p, and this is the displacement, which this one is moving from here to here. This is creating the displacement definition. And we can say that this is the deformation of an elastic body. For the rotations, we can write, let's make it clear. For the rotations, the same approximation. I'm going to write for theta 1. Again, this can be written as limit delta x is going to 0, delta v over delta x. We will get as a conclusion dv over dx. Look at here, not du. This is dv because I'm talking about the angular rotation. For the theta 2, I'm going to get this time du over dy. And for a deformation on a plane, we can say shear strain, if you remember. Gamma xy will be equal to gamma yx. Can be said that theta 1 plus theta 2 is equal to du over dx plus, I'm sorry, not du, let me erase it, dv. This should be dv. dv over dx and plus du over dy. This is shear strain in xy plane. XY plane. So I can show you the description. Like this. You need to study from the theory of elasticity notes. This one. For example, we got a one length of an element, the other length of an element. In some definition or some books, the people are showing like this. This one, the original element. And this one, deformed element, like this. Here, 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 here. Considering these, we can write now, sorry, let me write it. Yes, gamma yz is equal to gamma zy, again d omega y over dy plus dv over dz. Again, for the gamma xd and gamma zx is equal to d omega over dx plus du over dx. Yes, we almost completed, and we can say that this figure, this one, can be said that it is a derivation of the shear strain, because you can see from the figure, and it's also may sometime be equal. If it is equal, we can accept it here. Theta 1 is equal to pi over 2, and this one is also pi over 2, but sometimes it won't be equal. Because of that, you have to look at the moments to understand if it is okay or not. Moments around x, y, z should be 0. Yes. However, the strain displacement relations, we can give the expressions, and we can say that for large magnitude of deformation, instead of writing, let me find to you the equations. Yes, this is for all of the deformations. I'm talking about YZ and XZ plane before, but for now, large magnitude of deformation to describe the expression of strain and displacement. And finally, I have forgotten the ZX. Let me give it also. As this one is for ZX. Shear strains. These are normal strains. These are shear strains. And don't forget, xy is equal to yx, unless these equations will become from 6 to 9. Now it is 6. If they are not equal, and if the moments are not equal to 0, then the strain vector, like this, starting from epsilon x, epsilon y, epsilon z, and gamma xy, gamma yz, gamma zx, will continue if the moments are not 0 with, tell me, gamma yx, gamma zy, and gamma xz. So it was before 6 by 1, but if it is not equal, it will become 9 by 1. But if it is equal, there is nothing like that, so it is going to decrease to 6 by 1. So let me clear here. And we can say this vector, strain vector. And we can also write it in a way of rho, but if you write it like that, you should transpose the vector. How? The transpose of the system can be here, can be seen in here. X the same, y here, z here, x, y, y, z, and finally zx. We have created the transpose of this strain tensor. And the strain displacement relations before can be reduced to the linear relations, and let me give you the linear relations. These are the relations for linear, and we have reduced them and make the equations easier. And we can also tell these guys, let me write it. This is a von Karman strain displacement. Equations. And after writing this, I'm going to try to create the tensoral system of the strain vectors. It means I'm going to write it in the matrix form. So the matrix form can be written like this. This is a strain vector, and the open form we have written, if you remember, come here, look at here, du over dx, dv over dy, d omega over dz. These are the strains. Let me come back here. D, if you multiply it, du, and 0, 0. dv, 0, 0, and d omega, 0, 0. For the shear, remember, dv dx, du dy, dv dx, du dy. Coming back, du dy, dv dx. Okay? And for the second one, dv dz, d omega dy, and du dz, 0, d omega dx. It's the open form of a strain vector in terms of matrix definitions. And as I have told you in last week, for the linear, elastic, anisotropic, and homogeneous materials, let me repeat it again, if you remember. This one is 6 times 6. And let me continue. We have already talked about these, but I wanted to show you again. Yes. And we can also write something like that. Here. And Maybe I should write the names. I think you don't remember. This one, we can say orthogonal planes of symmetry. And for the orthotropic one, we got that one. And maybe the temperature effects, etc. Maybe I should give to you temperature affected one also. Yes. I think I should, if I should put here, can you able to see? I think it's okay. Maybe a little bit more. You need to separate them. Yes. For this one, I need to say that this mu is written different in here. You can say it's a Poisson ratio. You can change it like this. Some of the books write it in this way. And these are alpha, T. These are coming from the temperature effects due to the temperature changes. And you can also make here inverse if you try to find the stresses. Let me take these guys here and give you the strain components this time. Again, these are the same. It's not so important, but because we are using mu instead of nu, we can change the characters. Yes, and we can also say that here. Do you remember this one? It is very close to Lamé, constant of Lamé. And here we have used thermal expansion, coefficient of thermal expansion, don't forget it. The alpha used in here is thermal coefficient, thermal expansion. Yes, when you look at the two-dimensional distribution, I think today we have got no time to reach finite element, but I try to finalize because these are the basic equations of tensors that you are going to create during the class of finite element method for describing the stiffness matrix or the other metrics that we are using to identify the material behavior. So maybe you don't remember, we called also compliance matrix to that. Yeah, two-dimensional stress distribution. Let me explain it. It is much more simpler. If you are working in 2D model, you will decrease it here. Instead of 6 by 1, you will use 3 by 1 vector. And the above expression, or this one, can be written in a combined form, like this one. This is the combined form of the above equations. So, there is a few, maybe there are some, let me say, there are some very important issues, especially with the plane models. One of them is plane stress model. And maybe I should give you the equations of plane stress and the other one plane strain. These are the basics of the system. Let me write it. The simplest form of the plane stress, which means that you have got a very thin layer of material. For example, hood of a vehicle. We call it in Turkish kaporta. It's so thin. We are not using its thickness. So let me write in those type of materials. For example, balloon. It is very thin. We call that plane stress model. So sigma is equal to, let me extend the class about 10 minutes. I don't know if it's gonna be enough or not. Let me see. Sigma x, sigma y, and xy. As I told you, sometimes you can write in this because here these are very important, but regularly this one is much better. So xy. This is the vector of the stresses. And now let me write the, and we can also write like this. Vector is equal to the same idea, epsilon x, epsilon y, and gamma xy. Here gamma xy is equal to gamma yx. And again, I want to write the stiffness matrix, which is depicted by C, is equal to E Young modulus over 1 minus mu squared, and in matrix form 1 mu 0 mu 1 0, and for the shear 0 0 1 over 2 1 minus mu. And we have got again here epsilon z in here, which is minus mu over 1 minus mu in parentheses epsilon x multiplied by epsilon y. And this is called plane stress model. It means all out of plane stresses assumed zero. Very important. All out of plane stresses assumed zero. In plane stresses are here. We have got no sigma z because it is an out of plane stress. Let me write plane stress. Yes. And for the plane strain model, you can say that we have got a dam. You know who dam? Dam we call barrage. There is a water inside the dam, or you have got a pipe. You have got a water canal. It means something like that. Let me draw it to you first. For example, for the plane stress, the surface, it is very thin layer surface. There is no thickness. It's like a shell, and because of that, we have got, let me say, in plane yüzeyde, it means 1 or 2 or x or y stresses, which are sigma x and sigma y, and you have got a shear tau 1 2 or tau xy, but we have got no normal stress on 3 or z. It is plane stress model. But if you look at in a pipe which is carrying a laminar flow of water filled pipe, I am going to show you a cross section of it. This is a pipe, center of the pipe. Inside is filled with water. So when you cut the pipe here, for a simple one, you will get a scene something like that. I'm going to repeat it. The inside of the pipe, and it is filled with, again, water. If you try to create a solution, considering here the cross section of the system, but starting from 1 to 2, there is nothing changed. Everything is the same. When you are going here, everything is the same, all cross sections. So this is going to explain you plane strain model. Yeah, let me clear this. Plane strain model. Let me write the equation. The equations here is the same. So sigma x, sigma y, tau xy. These are just because of the simple model I'm talking about here. We make the system simpler for the 2D. And again, the strains, let me copy the same. But for this time, all out of plane strains assume 0. In plane strains, which are sigma x and epsilon x and epsilon y, and the shear strain gamma xy, we have got those strains, but we have got no any other like epsilon z, epsilon zy, xz. Here also we have got no epsilon z, and we have got epsilon z, but there is no others. Here the thing is changed. Let me write it here. For the plane strain model, we should express it inverse 1 minus mu squared over E in matrix form, 1 minus mu over 1 minus mu, 0 minus mu over again 1 minus mu, 1 0 0 0 2 over 1 minus mu. This is the description of plane strain model for defining the stiffness inverse. And like in here, in plane stress, when you hold the edges of a, for example, this is a part of a flex element, flex plastic, like a balloon. You cut it and you prepare an element like this. When you hold from here and here, and you try to create a tensile test, and here also, what is going to happen? Here we said that there is no thickness, but we have in real time, in real life. So when you create a tensile and hold and create like this, the thickness will decrease. It means we have got epsilon z because there is a deformation. In this model also, we have got the same thing is going on inside of the pipe, or some scenario like that. The same thing is going, but when you cut and get the cross-sectional area and definition, you can say that we have got a stress at the axis of z. So we can write sigma z is equal to mu sigma x plus sigma y. Yes, this is the basic definition of plane strain model. So let me give you a little bit more detailed ones. Because of that, I want to clear here. For the plane stress, the element shape or the approximation will be something like that. I'm sorry. Yeah, the shape is similar. 2D element, but there is a deformation in the thickness. Considering this, and we can also add the temperature effects. Initially, I want to write this stress form. This is the stress form. Again, the mu's are written different. It's not so important. And in strain form, let me give it to you. This is in strain form. And the others, epsilon z, and the other shears, sorry. Oh, sorry, something happened differently. Yes, we can also say that yes, for the plane strain, let me give you the figure first. A few different things, but I have already told it to you how the shapes can be. Let me make it smaller. A retaining wall is filled with, for example, concrete or soil, toprak, or here a dam, barrage, filled with water. The same. When you look in depth, this is x, y, and z. If you look at minus z direction here, like this, direction of here, it just continues the same, and the same in z direction also. So these are plane strain models. Let me give you the equations. We can say that the constitutive relation, elastic isotropic material, and I have to say that again here, epsilon z, gamma yz, and gamma cx should be equal to 0. And if I try to write those guys in terms of strains, let me change the equation again. In terms of strains, the equation and matrix equations will be like this. Yes. So, for make it clear, let me draw something like that. Yes. Okay. for today, our class is over. I think for the next class, we are going to start with the finite element method.